In this video, we'll look at how to implement piecewise interpolation in MATLAB. After studying this video, you should be able to use MATLAB to implement piecewise interpolation using linear and cubic splines. Also, you should be able to use MATLAB to calculate cubic splines with clamped and not-a-knot end conditions, including finding the spline coefficients. So let's look at MATLAB's spline function. This is the built-in function for calculating spline interpolations with MATLAB. Here's the syntax. In this syntax, the x and y, this is our data, and xx, this placeholder, is the x points where you want interpolated y values, and those y values, could be 1 point or it could be multiple values, and those y values are output to the main output, yy. The default here will use not-a-knot end conditions, but if when you give it data, if y contains 2 more values than x, then the spline function will interpret the first and last values in y as the derivatives at the endpoints. So this is how you would use the spline function to implement clamped end conditions. Remember, clamped end conditions are how you explicitly set the derivative values at the first and last points. There is no option for natural end conditions. You would have to do this manually. So again, that output yy is a vector of results of the spline interpolation at the points xx. Notice here we don't have an output of the spline coefficients, but there is another way to use the built-in spline function to calculate the spline coefficients. And to do that, we just call the spline function again, but the key difference here is no x values to interpolate at. So we just give it, the spline function, the x and y data. And again, if the y data has 2 more elements than the x data, those first and last values can specify derivative or clamped end conditions. So when we call this with only 2 inputs, the output is a data structure that defines the piecewise polynomials that make up the spline. So here's an example of how this works. So here we'll set up, here's data x, we'll set up some data points, x being integer values from 0 to 10, and then we'll sample the sine function. So we're going to sample sine at those x values to generate some data, and then use the spline function to fit a spline to that data. So we're going to approximate that sine curve with a cubic spline. And you see we haven't given it any specific data points here. This third input is left out, and so S returns a data structure. The form, this PP, stands for piecewise polynomial. And the breaks, these are the knots. Recall that's the values of x, 0 to 10, so those are the breaks. And then coefficients are in a 10 by 4 double, because these are double precision numbers. And so we have 11 data points, so we'll have 10 intervals. So we have 10 rows by 4 columns. Just like we'd expect, we have 40 spline coefficients. Again, that's 4 times n minus 1, where n, in this case, is our 11 data points. Now, you can double-click on the data structure S in the workspace to bring up the variable editor to see what the spline coefficients are, or you can basically unpack this data out of S to get it into standard double precision variables using another built-in function called UNMKPP, which actually stands for unmake piecewise polynomial. And when you do that, the first output will be the knots, the location of the knots. So that would be the 0, 1, 2, 3, up to 10. And the second output would be that 10 by 4 matrix would go into a variable called coef. You can call that variable whatever you like, of course. And that variable now stores all of the spline coefficients that MATLAB used to fit a spline to the XY data. So if you want to access the actual spline coefficients, you first call the spline function without giving it X data to interpolate to, and then use the unmake piecewise polynomial command to pull the spline coefficients out of the data structure that MATLAB returns them in and bring them into just a standard double precision variable. So MATLAB has another function for general one-dimensional piecewise interpolation, and that's called the interp1 function. And the way that works is still the same basic approach where the first two inputs, x and y, are our given data that we're using for the interpolation. xi, the third input, that's the points or point we want to interpolate to. And then method is a third input that just defines what type of interpolation we're going to do. And there's 4 options for the method. The first option is called nearest neighbor interpolation, and I'll give you an illustration of what that looks like in a minute. Then there's linear piecewise interpolation, so this is a linear spline. The spline option is only for not a knot cubic spline interpolation. If you want to use clamped in conditions, you need to use the built-in spline function. But if you want not a knot in conditions, it's the exact same thing to use interp1 with the spline method as it is to use the spline function. And then the last option is this thing called piecewise cubic Hermite interpolation. And this is basically a modified cubic spline, and I'll show you what that does here in a second. So here's an example of interpolating 5 data points with those 4 different options. So the nearest neighbor, you can see it's just breaking it up into constant steps. So over the range of each function, it just goes to the nearest point. So here we just have basically stepwise functions. Here's the linear function. As we might expect, we have a line between each point. And here's our spline option. And one thing we see with the spline option that still we have, because it's a cubic, is we still have a little oscillation here that may or may not be reflective of the actual data. But since these 2 data points are basically, and you can see them with the nearest neighbor, these 2 data points are, the y is the same value. And it might be that the data should actually be constant all the way across instead of dipping around like this cubic does. And the cubic Hermite interpolation is basically a modified spline algorithm that looks out for that. It basically tests the data to see if it's what's called monotonically increasing. So in regions where the data is monotonically increasing, which means the next value of y is greater than or equal to the previous value of y. So here we have y2 is greater than y1, y3 equals y2, and then y4 is greater and y5 is greater. And in that case, what it will do is it will use a cubic for that first interval, but then it's going to damp the oscillation by using a constant interpolation up to the next y value. And so the cubics that the piecewise cubic Hermite interpolation uses are slightly different from the spline cubics. And basically this is a good option to try if spline is giving you unwanted oscillations. Remember, the spline approach it reduces oscillations, but it doesn't fully eliminate them depending on what the data is doing, because we are still using a cubic. So let's look at an example MATLAB script to investigate these different approaches. And in this script, what I'm going to do is use sample data from the MATLAB humps function, and this is a built-in function. And it's there in MATLAB basically for testing numerical algorithms and how they behave with this function. And we'll look at it here in a minute, and I'll talk about why it's there. And so I'm going to generate sample data f of x at points from 0 to 1 on an interval of 0.1 and use those to interpolate to a finer data spacing of 0.01. And we'll use the following approaches, all of which we've talked about. Piecewise linear spline. So here's a linear spline. A 10th degree polynomial. This is a standard direct polynomial interpolation. Remember, we have 11 data points. So 11 data points mean that an interpolation of all 11 data points would happen with a 10th degree polynomial using the polyfit command. And then two spline options. The first spline option is just using a not spline, the default spline, and I just used interp1 for that with the spline method for interp1. And then to do a spline with clamped in conditions, and here we're assuming df dx equals 0 at the first and last points. And we tell the spline function that by basically adding them as a new first value and a last value to the y data vector. So this goes into our y or fx input to the spline function when we go to do that spline interpolation. And I've left off the plotting commands. That's what's below. I would recommend you download the M file and work with it and make sure you understand how all of these functions are working and how the plotting commands work. And so let's look at the results. So here's the results. So you can see the main humps function going through, and again, the reason that this is a nice function for testing numerical algorithms is because it has a steep peak here with a quickly changing first derivative, and then as we go down here it has a very slowly changing first derivative with a shallow peak. And so those two different behaviors of the function can capture different problems in a numerical algorithm might have. So we see, like we might expect, and we actually saw the same figure before, the 10th order polynomial has pretty wild oscillations at near the endpoints of the range. And then we can see the piecewise linear here is the black dots, and it's just connecting the dots between the stars, which are our sampled data. And the not spline follows fairly closely with the humps function, as does the clamp spline. And if you look closely at this, and again I would encourage you to download the M file, run this code, maybe try and see what happens if you change the number of points, and look closely at the file, you'll see the differences in the splines are really only at the endpoints. And again, that's because the only difference between these two splines, the not-a-knot and the clamped, is those end conditions that were applied to get those last two equations needed to solve for the spline coefficients. So download this M file and play with it in MATLAB and make sure you understand these various interpolation approaches. And that concludes this video.